Correct.
Yes, sir. And
Okay, welcome to this lecture. Today we are going to discuss the very important and useful topic of the queuing theory, that is known as performance measure of the queuing theory or queuing models. Whenever we talk about the performance of the queuing system through its operating models, then there must be certain criteria so that we can measure and assess whether the system or the model is working properly or not. If any model is working properly, what does it mean? It means that whether we are providing the optimal service to the customers or not. So whenever we are intended to discuss the performance of the queuing model and queuing system as well, it means that we are going to assess and evaluate the performance of the service. Means we are looking at for the optimal service, which must be given to the customers who have entered into the service. Now, here question arises that how we can assess what is the formula, what is the method which can be designed and developed so that we can measure the effectiveness. So I would like to make clear here that I would like to make clear, please mute, somebody is making noise, please mute it. So what are the terms so related to this performance measure? There are certain terms which are related to performance measures, and these terms are popularly known as the performance measures and operating characteristics. Another popular name is operating characteristics, and another name is this measure of effectiveness. I would like to show you how this measure of effectiveness is working. So there are three important titles for this performance measure. One is the performance measure itself. Another is operating characteristics. I would like to show you here. So this is the criteria which we intend for the measurement, and this through this criteria the service is quantified, the optimal service is quantified or measured. Optimal service is quantified or measures. What does it mean? It means that we need to have some finite number, finite quantity, finite amount, so that by looking that we can arrive at certain decision making. Decision making is what? That decision making will be related to the performance. Means if see the quantity is high, it shows that the rate and quality of the service is not good. So that is the inversely proportional, or that is not proportionate to the quantity of the customers available in the system. So these names which I would like to show you here, that is one popular term is the measures of effectiveness. Measures of effectiveness. That is abbreviated like MOU. MOU. Measure of effectiveness. So one is MOU and the another is PM. Another is PM. PM means performance measures or measures of performance. If you want to write is MP, this may be MP, measures of, that is measures of, or MO if you want to write MOP, MOP, measures of performance, measures of effectiveness, same. And this is also very popularly known as operating characteristics, OC. Look at this very abbreviation, OC, operating characteristics. So either we say the performance measures or MOP or MOE, MOE, or we say OC. These are same and these are simply measures or a method of quantification that is used in the giving model. So these measures are used to assess the performance of the model. And model is what? Model is the operating form of the giving system. And therefore, when we talk about the model and its performance, it means that we are talking about the giving system and its service. So first very measure is expected number of customers. This is the expected number of customers in the system. What does it mean? If you remember the first and very beginning outlook of the customer is that he or she wants to know that how many customers on an average are available in the system or entered into the system where they have gone to take the service, to receive the service. So expected number of customers in the system means it has two parts. One part is how many on an average persons are standing in the queue and how many are being serviced. So both are the customers who are or that are being serviced. That is one part. Suppose there are 3 servers, then 3 customers are being serviced, but still they are in the system. They are not departed from the system and therefore they are also in the system and they are considered to be waiting for their service, though they have already engaged and their service is already started, but that number of customer is in the service, that one. And another part of the number of customers is who are standing in the waiting line or queue. So this is simply represented by LS, the length of customers in the system, length of customers in the system, or expected number of customers in the system, both are same. both are same, and it is expected length of customers in the system, and which is computed by a formula. Symbolically we write this thing: expected number of customers in the system is number of customers waiting in the queue, as I explained right now, just now, and number of customers being serviced in the system. So it has two parts. One is this, and another part is in the queue. So how we can compute it? How we can compute it? So mathematical design or mathematical structure for computation of this performance measure is given as expected n is equal to ls is equal to sum over n ranging from 0 to infinity. Rather, if you have any objection, we can say this is 0 means empty. So we can say here, if you have any problem, we can put here 1. So it is ranging from 1 to infinity, means number is ranging from 1 to infinity. So this is, if you remember, this is a very popular formula of the mathematical expectation. What is the formula of the mathematical expectation? Why we are using the mathematical expectation here? Why we are using the term expected here? Because the variable may be in the form of numbers or maybe in the form of times, interarable times, and the number of customers arriving at the system. One is the discrete, another is continuous, but both are random. I am again to share with you this very concept that whenever the variable becomes random, we talk about the expected number or expected amount. It is just similar to the average. So in the average and the expected has no difference. Only the difference is that when the variable becomes random, we have the formula of mathematical expectation. If x is a random variable, then expected x is what? Expected x, if you remember, and this is very popular formula, we have time and again uh, explained this very point: the sum over i, i, I is ranging from 1 to infinity or 0 to infinity, 1 to infinity or 1 to whatever it 1 to n, whatever it is, 1 to n, and here the xi is here, and pi into pi. This is the mathematical expectation. Look at this very point and thus observe this very point, that here n is the discrete random variable. This is n is here discrete random variable, a discrete random variable. N is discrete random variable. Here n is naturally, it looks like natural number, but it is a discrete because of the natural counting. It is discrete, but here it is random. It is not deterministic or fixed, and the corresponding probability is Pn. So this formula will be used, and what will be the exact value of the En, expected number of customers in the system, that will be calculated, computed for the particular specialized model when we are going to discuss the model. Because for different model, this expected number of customers will be different. So this is the first one and very important measure. Second one is the expected number of customers in the queue only. So why we are why we are making emphasis on knowing the expected number of customers in the system. Suppose number of customers in the system is very high, what does it mean? Number of expected number of customers in the system is very high, or in the queue is very high. It shows that quality as well as rate of this service is not satisfactory. It is not in proportion to the number of customers who have entered into the service center. Means if it is too long, the line is too long, what does it mean? It means that demand is very high. Demand of that service is very high. It's okay. It is a point of satisfaction. It is a point of complacency for this service provider, but it is not a point of complacency for the customer or for the outsiders who are intending to have the service. And therefore, we from both point of view, we attempt to compute the size of the length. The persons who have entered into service and they are getting the service a little bit or to the major extent, they are satisfied because they have entered the service. They are being serviced. So they know that after the service, they will go out of the system. But the persons who are standing in the queue, they are still desperate. They are still waiting for their turn. So therefore, it is also important to have the expected number of customers in the queue. Only queue. We are interested in only queue because the persons or the customers who have entered into service, they are to major extent satisfied because they have entered already and their service is going on. So if we are intended to know the number of customers in the queue, only exclusive of service, excluding, it is written here, excluding number of customers engaged or entered into service. This is excluded. Excluded here, this is exclusive of the number of customers who have entered into service. So we obtain this performance measure. It is similarly represented by expected M, M is small m, and LQ it is similar. This is only for Q, and S is for system. And the purpose why we compute this, it is well known. So next one, this formula, let us look here. This formula, expected M is equal to sum over N. Sum over N is ranging from C plus 1. I mean, if it is C is equal to 3, here, the formula first you look at N minus C, probability Pn, where C is the number of servers working in the system. C is the number of servers. C is the number of servers means it is ranging from C plus 1. If server is C is equal to 3, for example, C is equal to 3, C is equal to 3, then N will start from here 4. It will be 4. C plus 1 means 4. So this summation will range from 4. Okay, why this is happening in this way? Here is one question I am putting before you all. That N is the number of customers. And what is C? C is the number of servers. Suppose C, 3 servers are working, 3 doctors are working in any system. So N minus C, N is the number of customers, C is the number of doctors or the servers. So how we can subtract the C from N? because both are different things. How subtraction is taking place, what is the justification and interpretation of this? So interpretation of this is that if C is the number of servers, so as many as number of server, that many will be number of customers. Because if we say that there are three servers, it means that three servers are already engaged for three customers. They have engaged three customers. Three customers. So if there are three customers who are in service, then we will exclude these three. We will start from where? We will start from four. And therefore, this C is subtracted. This is not the doctor, not the server. This is number of customers, because number of server is equal to number of customers. One server will engage one customer. Two servers will engage two customers, and three servers will engage three customers, and therefore these three customers are being serviced, and therefore since it is a inclusive of this service, and therefore n minus c formula is applied. And what is the probability? Probability will be Pn. N is general. N means number of customers. If you are interested in fourth, you are interested in fourth, I mean customer, then this will be P4. If you are reaching the 5, this will be P5. So this N, you may not, you may think at one point of the time, you may think that n should also be n minus c. No, no, there is no need for making it n minus c, because n is of general character. So this is the another formula which is important, and this is denoted by m. So we come to the next measures of effectiveness or operating characteristic, that is popularly known as 3 is C3 means this. So the fourth one is third. How this is the second? No, this is third. This is this is third is what? Expected waiting time of customers in the system. This is the an average amount of the time which is spent by a customer. This is very important here. By a customer. By a customer. Average means for per customer. I was just writing is the, then I remember no. The average, whenever we compute the average, then average is related to the individual, single individual. If we compute the average height of the class, we say the average height of the class, but that height, particular height, suppose this is 5.3, then average height of the class is 5.3. It means that each and every student is having the height 5.3. So this is per customer. individual customer. In the system, including the waiting line, including that time is standing in the waiting as well as in the service. This is denoted by WS and computed by the formula. I just take you a very popular formula. WS, so is it, I think, clear? WS is the average waiting time which is spent by a customer in the system. In the system means including the time in which the customer is given the service as well as including the time for which customer is standing in the queue. There is a very popular formula with a popular and famous mathematicians. I don't know whether you have heard this name or not, but today you will hear this fellow who is very, very old nowadays, still he is alive. This is one formula. This formula is known as LS is equal to length of Q in the system is equal to arrival rate into WS waiting time in the system. So by choosing this formula, we are interested in WS, but already we have computed LS, this LS, length of the queue in the system. And if we divide by the arrival rate, then we will have the WS is equal to LS upon lambda. So how this formula, to whom this credit should be given, that formula, popular formula through which we can compute the expected waiting time in the system, this relation is given by the Little's. Little's full name is Little's formula. This is known as the Little's formula. For Gavaskar, a little man, the Gavaskar has got the title of the little man in the field of cricket, play a game of cricket. So similarly, if you want to see the height, weight, etc. of this professor, so but that is not because of the height. Gavaskar was given the name little because of the height, but it is his title. This professor is title is Little, and his name is John and Little. If you want to see his bio sketch, you can see on the Google. But sufficient information I am providing you here. And he was a MIT faculty, professor in MIT, Massachusetts Institute of Technology, top 5 institutes of the world, or rather you can say first, second, third, top 3 or top 2. It is in the among the top 3 institutions of the technology. The oldest is one of the oldest institution of the technology. We look upon, if we look towards its report of the technology if something happens. And recently, if you remember, the Arogya Setu was commented by the report reported by the MIT that it is not sufficient to protect the private data of users. So it was given by the MIT. I'm surprised. I'm wondered that we have a lot of IITs, reputed IITs. Their name is so high, but still we do not have any good apps like Zoom, like Google Meet, like GoToMeeting, like this or that, which we can use as well as other countries of the world can use. But name is so high, but performance is not according to the international standard. Anyway, that is not our business, that is not our cup of tea here to discuss all issues. I would like to tell you only that you look at the fellow date of birth 1928 till today. I was thinking he is no more, but he is nowadays 92 years and he is a OR researcher, and we are studying his researches made by his made by him during his tenure of active researcher, and still if he is not alive, we have the moral responsibility to study this topic, and from that point of view the professor will become immortal. His thoughts, his researches will be immortal. So similarly, now the next one is this number we can change here using the little law. This number third. So this is third. This is fourth is okay. Okay. Fourth is what? Expected waiting time. Expected waiting time in the system. Time in waiting line. Okay. Waiting line, not system. This is what. This is again the expected means an average amount